A planet can remain world-sized while catastrophically evaporating, its star-stripping material into space. These are exoplanets, planets orbiting stars beyond our solar system. Some circle so closely that a complete orbit takes less than an hour. At that distance, stellar radiation and heat pour onto the exposed planet. The energy can drive atmospheric gas and other surface material away from its gravity. Researchers detect the world when it crosses its star, briefly dimming starlight. Doppler spectroscopy measures the star's gravitational wobble. Together, these signals reveal the orbit and let astronomers investigate material escaping from the planet. The consequence is physical, not metaphorical. A planet can change dramatically under stellar conditions. Its atmosphere may thin and its escaping material can become evidence of a world in transition. A planet is therefore not necessarily permanent. Even a world-sized object can be reshaped by the star it orbits. A cube has 6 square faces, yet it can be unfolded into 11 distinct flat patterns. The solid looks singular, its possible nets are not. Each face is a square and neighboring faces meet at right angles. The cube also has 8 vertices and 12 equal-length edges. A right angle is 90 degrees, so every fold has a fixed geometric target. A net keeps all 6 squares connected while laying them flat in one arrangement. Fold every shared boundary upward to a right angle and the faces can return to the cube. But connected is not enough. Some layouts fold into the solid without overlap, others place squares where faces collide or fail to close. A valid net closes cleanly with no gaps between faces. Testing the possible connected arrangements leaves exactly 11 valid nets. They are different flat layouts of the same 6 faces, each rebuilding one cube when folded. Voyager did not record sound traveling through empty space. Frederick Scarf's instrument measured plasma waves, then converted their frequencies into hisses, pops, and whistles. Plasma is electrically charged matter surrounding the spacecraft, not ordinary air. Its particles can oscillate, creating patterns the instrument can detect as changing electric signals. It is a gas-like state of matter whose particles carry electric charge. Scarf led Voyager's plasma wave subsystem as principal investigator. The instrument measured those oscillations rather than microphone vibrations. Frequencies within the acoustic range could then play through a conventional loudspeaker. A planetary bow shock forms where the solar wind first encounters a planet's magnetic field. Voyager's measured signal grew stronger there, becoming a roar-like sound. A vacuum still carried no ordinary sound wave to Voyager. Instead, plasma measurements became audible recordings. For Saturn, the data were divided into 16 frequency channels and played through a 16-channel music synthesizer. People could hear a data stream from the spacecraft. A famous mirror problem resisted every straightedge-and-compass construction, so Leonardo da Vinci is credited with approaching it using a mechanical device instead. The task is to find where a ray hits a spherical mirror, then travels between 2 given points. In 2 dimensions, the reflection point lies on a circle's boundary. At that point, incoming and outgoing paths must make equal angles with the normal, the line perpendicular to the mirror. That rule identifies a reflected path, but ordinary geometric tools cannot construct the point. According to the supplied account, Leonardo used a mechanical linkage rather than a purely mathematical construction. Later solutions used conic sections, curves such as hyperbolas, then described the point with a 4th-degree equation. The optical question therefore has 3 roots: geometry, a machine enforcing the reflection condition, or algebra. Each aims at one concrete location on the mirror where light travels between the 2 points. Air pollution is linked to higher risks of miscarriage, stroke, and dementia, even when the pollution is too small to see. Pollution is not one substance. It includes gases such as ozone and nitrogen oxides, plus particulate matter, microscopic solid particles, and droplets suspended in air. Size changes where particles can travel. Fine PM2.5 is smaller than 2.5 micrometers, while ultrafine particles are 0.1 micrometers or smaller. These particles can move deeper through the lungs and the smallest can reach the bloodstream. Once particles or their effects reach beyond the lungs, the body can respond with inflammation and oxidative stress. Particulate pollution is strongly associated with cardiovascular disease, including stroke, and with respiratory disease. The exposure is also associated with dementia and pregnancy complications, including miscarriage. Cleaner cooking, emissions controls, and less fossil fuel combustion can reduce the particles people breathe, turning prevention into a measurable change in exposure. A little-cited 1938 paper by Arthur J. Ruhlig recorded observations of deuterium-tritium fusion and helped direct Manhattan Project attention toward investigating the process. Deuterium and tritium are two forms of hydrogen. Fusion means their nuclei join, producing a reaction that must be identified through its measurable output. That distinction matters. The nuclei are too small to watch directly, so researchers rely on emitted signals. In August 1938, Ruhlig published Search for Gamma Rays from the Deuteron-Deuteron Reaction in Physical Review. The paper recorded observations linking a gamma ray signal, high-energy radiation, with the deuterium-tritium fusion process under study. Those observations prompted the Manhattan Project to investigate deuterium-tritium fusion. The paper's influence came from a recorded experimental signal, not from a sweeping claim about every fusion reaction. Afterward, Ruhlig developed instruments for studying the atmosphere, led a radiation department, and worked on nuclear test diagnostics. His later work kept turning invisible physical conditions into instrument readings. Stanley Plotkin, pivotal in developing the rubella vaccine, wrote a major textbook because vaccines had become a field of medicine in their own right. Plotkin said vaccinology, the study of vaccines, grew from infectious disease but became more than classical infectious disease. Immunology supplied its basis, not its identity. In 1988, the reference appeared under the simple title Vaccines, 633 pages built by 42 experts led by Plotkin and Edward A. Mortimer, Jr. Plotkin wanted one source where readers could find answers to questions about vaccines. Later editions expanded beyond individual vaccines into new technologies, special groups, and public health and regulatory issues. Their coverage included vaccination for pregnant or immunocompromised people, plus policy and oversight. Later editions added new contributors and hundreds of pages. A field becomes visible when its questions need a dedicated body of knowledge. Plotkin's first volume made that need tangible, 633 pages giving practitioners and students one shared medical reference for specific vaccine questions. The original type specimen of Cynodon gibbus may have vanished in a bombing raid. If so, one preserved fish once anchoring its scientific name was lost with it. A type specimen is not meant to be an average fish. It is the particular specimen formally associated with a species name, usually preserved in a museum research collection. Taxonomists compare newly examined fish with that preserved reference and its original description. This fixed point helps determine whether a specimen fits Cynodon gibbus or another named species. If the holotype is gone, a lectotype can be chosen from surviving original material. If none remains, a neotype may be selected, but only when the rules allow it. So a fragile museum object can carry a fish's name across generations of research. Even when loss is uncertain, catalogs, descriptions, and carefully preserved material determine what can still be identified today.